Perfecto. Así que esta sesión es de aprendizaje e inferencia. This is our learning and inference session, and so I think we're just about to kick things off. Thank you. So presenting first for us will be Santiago Cortés Gómez for inference under constraint selection bias. Thank you so much.
Thanks, Francisco, for the introduction. So, without further ado, this talk is called Inference Under Constraint Selection Bias. It's a work done by myself in company with my collaborators, Mateo, Dulce, Carlos Patino, and my advisor, Bryan. So, statistics and machine learning has increasingly been used to ground decision-making on data, particularly at the policy level. For example, to compute, to understand the risk factors driving homelessness, or to understand an increase in observed incidence for a particular disease outbreak in public health. Particularly in the case of the COVID-19 outbreak, health institutions had access to data sources such as insurance claims and health records. With those data sources, statistics of interest could be computed, for example, hospitalization rates, and further, these hospitalization rates could be broken down by race and ethnicity groups. So one question that was relevant during this outbreak was trying to understand if there were disparities in the risk of hospitalization when computed for minorities and then compare against those risks for white populations. So in the plot that I'm showing right now in the slide, if we compute this hospitalization risk, this ratio of hospitalization risk, this marginal average increase of hospitalization risk, and is left to the red dotted line that is seen in the plot in the slide, it means that indeed there were disparities and indeed there was an increase in hospitalization risk for these minority groups. So when we do that with the data, we found that that was indeed the case. However, we know that unfortunately healthcare access is driven by interactions of several variables, some of them geographical and some of them based on socio-economical background. And for example, in the case of the United States, we know that people that lack health insurance, they are going to avoid going to the hospital unless they are really, really sick, right? And that means that we are going to have underreported infection rates. And that's particularly insidious in our case because infection risk is the ratio of seen hospitalizations over infection rates. So these data points are biased, and furthermore, they are biased by an interaction of the outcome, whether or not you get really sick, and these covariates. So it begs the question, though, what mechanisms underlie racial inequalities in COVID-19 outcomes? This is going to be a motivating example of this talk, and I'm going to refer to it throughout all the talk as well. Every time I do so, it's going to be signaled by a gray rectangle in the slides. So, what's the challenge? As I told you, when we're trying to ground public policy data on observables, distribution shift is not only possible, but inevitable. As I already told you in our example, we have data that is polluted with selection bias because every data point we see it because of some correlation between the outcome, whether or not you get sick, and variables driving the access that you have to healthcare. What do we want to do? We want to provide robust estimates to be able to produce statistics using data polluted with selection bias, and we want all the assumptions we do for building our mathematical scaffolding to be able to be traced back to data. That way, stakeholders can hold accountable our model. So, this talk is going to start by introducing the formal definition, the formal statement of the problem. Then I'm going to walk you through our solution, and finally, we are going to circle back to our motivating example. So, We're interested in estimating a quantity f from distribution P. Distribution P is the ground truth distribution that can be any data at the national, state, or county level that we're interested in. For example, the United States population or the population of San Luis Potosi. But we have only access to n data points from distribution Q rather than P. Distribution Q, these data points are the insurance claims or the health records that we have access to. And it begs the question, what can we say about FP? So the answer is nothing, but of course it will be a short talk if that's the whole story. We can say some more things depending on the assumptions we made on P. So the usual suspects to solve this type of problems are sensitivity analysis and distributionally robust optimization. These frameworks are very interesting and have very elegant theoretical properties. However, they often rely on assumptions that can't be tested on data. For example, in the case of distributionally robust optimization, we need the distance between distribution P and Q in this space of distribution that is rarely, is not feasible to compute in our case. And well, that kind of sucks because again, we want our assumptions, our design choices, our engineering choices to be able to be traced back to data, to observables. And this requirement is not so crazy to think. Like if we think about all the available data that we have access to, for example, census data or studies run by non-governmental organizations, well, that's a lot of information that kind of says something about P. But of course, it's not as straightforward as it seems because the catch is that this data, it often presents itself as aggregations, as expected values of functions and covariates that we don't have any control of, right? That's what I denoted as G, and this data that I'm talking is what is denoted as a green expected value on the slides. So, furthermore, the issue is, for example, making a reference to our running use case. I want to estimate the hospitalization risk, but I only have access to unemployment rates or some income information. So how can I relate those two quantities? How can this inform how FP looks like? Well, the idea is that it constrains the type of distribution shift. So we're going to produce a bunch of solutions, and the key thing to remember is all this solution has to be consistent. So with the data that we have access to. So more formally, let denote as theta 0 as the ratio between the densities of distribution P and Q. Of course, if we had access to theta 0, this problem will be trivial. And also, because theta 0 is the true ratio, we know it has to fulfill the constraints that are currently shown in the slides. So what's the idea? Every possible solution, every possible estimate that we produce for theta, and theta is the way that we're going to parameterize our solutions, has to fulfill this set of constraints. We are going to denote this set of feasible solutions, of feasible thetas, as big theta. So what happens? Every time, every theta that we obtain, when we compute f using q, it's going to give us a value. By construction, because theta 0 is one of these feasible solutions, we know that fp has to lie between the minimum of such values and below the maximum of such values, right? So I want to stop here to highlight the fact that this is the price we're paying for our assumptions, and is now, instead of a point estimate for FP, instead of a number, I'm giving you a set, I'm giving you an interval. And yes, this interval may be vacuous if the bounds are like infinity, but often enough, if you have access to the right data, you actually have a meaningful set for which evidence-based policies can be derived. So, let's go to our solutions. There are two axes that I would like to mention. So first is the computational issues, and then the statistical ones. So the computational issues are regarding how do we compute the solution of the optimization problem that define these intervals. And the statistical ones is, so far I have been talking about computing a number out of a distribution, but we don't have access to a distribution, but rather to a sample. So how an estimate from the sample is related to the estimate that we're interested in computing. So I'm going to start with the statistical issues, and of course, let's start with the simplest case. F is a convex estimate, and for example, the expected value of some function h. So I'll define the population level problem as the optimization problem that defines the extreme values of these intervals. And when I say the population level problem, I mean this optimization problem is stated using expected values. This in contrast with the sample level problem that is exactly the same, but instead of expected values, I'm using the empirical means computed with the sample of Q that I have access to. So what we prove, based on a seminal result by Shapiro in a stochastic optimization, is that the minimizer of the sample level problem converges to the minimizer of the population level one. Furthermore, it does so in a central limit theorem type of way, which is great because that means we are allowed to do inference, produce p-values and confidence intervals or high probability bounds. However, this work was motivated by able to say things about coefficients of regression models, and these not only are not convex, but some of them have the more insidious problem that do not even possess a closed form solution, right? For example, in the case of a logistic regression. So what can we say about them in this case? Coefficients of regression models can be framed as a more general class of estimates called M-estimators. M-estimators are the minimizers of the expected value of some function of interest, like log likelihood. Again, we managed to prove that even in this setting, the minimizer of the sample level problem converges to a minimizer of the population level one. And furthermore, it does so in a central limit theorem type of way. This result, the intuition behind this result is just, it's based on a generalization of the delta method applied for empirical processes, a special class of empirical processes then usually known as a Dunker class. So finally, let's visit our computational strategy. This was way simpler. We just used the all reliable projected gradient descent. There was some details that we have to be mindful of, and it was essentially guaranteeing differentiability throughout the sample level problem for the M estimators. So finally, let's wrap up this talk by going back to our example. We are interested in computing the average marginal increase in hospitalization risk in minorities with respect to the wide population. In order to do so, we have access to an insurance claims data set. Again, what's the issue? Our estimate is biased, and we don't know if it's because of infection rates. We do know that because of the healthcare access is what in part drives this bias, as people that are not as sick, that only have mild symptoms, are going to avoid going to the doctor. So what are we going to use as constraints? We're going to use serology studies on COVID antibodies. So what are serology studies? Serology studies is just laboratory tests that look for the presence of antibodies in the blood, in this case, COVID-19 antibodies. They can be like, because the CD, if there is such presence of antibodies in the blood, it means that you had the disease, that you were contagious by the disease, and because the CDC run these studies at a large scale, they can be used as proxies for the true infection rates. So this is our final result. So let's stop here let me try to convince you why this plot is different to the one that we saw at the beginning of this presentation. So first, the obvious, we are looking at intervals rather than points, but that's what is important. All the intervals are left to the red dotted line, or right in your case, which means the designer, because of our framework, that implies that the true estimate, FP, is also left, of the red line. So we do know that there was indeed disparity on outcomes, disparity on risk, on hospitalization risks, and furthermore, because Now, like our constraints are our infections, we know that the reason behind this bias is not the underreported infection rates, but rather the covariates that we were conditioning for. In this case, age, income, and the presence of some comorbidities, which is great because now we have a statistical evidence to perform, to justify some targeted intervention and give actionable feedback in order to devise some public policy. So, what are the takeaways? The first one, when we are grounding data for policy making on observable, grounding policy making on observable data, we are always going to suffer from selection bias. This is an unsolvable issue unless you make some assumptions, and we have a lot of available data, albeit, it has to be said, it's often come as aggregations. And finally, expressive inferential frameworks, such as ours, allow us to include domain knowledge and scientific expertise that allows to inform ML systems. So thank you very much for listening. I'll take questions now.
Thank you so much, Santiago. Incredibly interesting talk. Are there any questions from the crowd? I mean, if not, I might have a maybe simpler question. So much of the mathematics might have gone over my head, but like I saw these intervals at the end, and I was wondering if, thinking about policy, for example, is there a way of getting types of samples that you're thinking about samples as a resource where you might be able to make the intervals smaller? Is there a way of kind of like targeting or having like the best type of sample in order to maximally reduce
like
size?
it's actually a difficult question because we throughout the talk, like the data that we're observing are these expected values of function g, and that's a very formulation. So depending on how g looks like, it also is going to alter how wide the interval is. But in essence, is the better your constraints are, the more informative they are, the tighter the interval will be, regardless of the approximation that you use using like the empirical means. So yeah, like and also like conversely, if the constraints are independent of the values that are driving FP, then you are not going to have anything, right? You are going to have vacuous bounds.
Thank you. Any other questions? We have time for maybe one more. Well, if not, then let's give another round of applause to our speaker.